All right, it's Professor McDonald answering this question, which has been a popular one. So I thought it would be a great one to make a new video for. This says solve the following system of equations with the substitution method. And then we have a place where we can enter the ordered pair if we have an ordered pair as an answer. And this would be typically systems of equations usually have one ordered pair answer where the two equations intersect. And this is when we have two linear equations, which we do in this case because we see that x and y are both to the power of 1. So these, if you graphed them, would just be two lines graphed on the same rectangular coordinate system, and they would intersect in one point, or it's possible they could be the same exact line and intersect everywhere, or it's possible that they could run parallel and not share any common points. So those are special cases when they either are parallel or if they're the same line. Those are special cases. They're less common in these types of problems, but it can happen. Down here it says enter your answers as integers or as reduced fractions in the form a over b. If there is no solution, okay, so if there were no solution, that would be the case where they were running parallel, right? So two lines that are side by side and never cross. If there is no solution, then you type DNE, meaning does not exist in each blank. If there are an infinite number of solutions, so instead of just one place where they intersect, if these two equations actually turn out to make the same line on the graph, then they would be intersecting at all points, and we would just need to write the x coordinate and the y coordinate in a way that expresses the relationship between x and y. And there's two ways we could do that. We could do it in terms of x or we could do it in terms of y. Now, if you continue to read down here, after it says, if there are an infinite number of solutions, specify their form in the blanks in terms of, in this case, it says do it in terms of x, right? In other versions of this question, it could ask us to do it in terms of y. So we'll look at both ways of answering this question. So first we'll look at how to do it in terms of x and then in terms of y. Okay, so I think I kind of gave it away here that this is one of the special cases. This is where there is an infinite number of solutions. But why should you know that? Well, here's how you would know. You would have to follow the directions first of all, solve the system of equation with the substitution method. And if we do that, the substitution method says, solve one of the equations in the system for a variable, okay, and then substitute into the second equation. So what that effectively does is it gets rid of one of the two variables so that we have only one missing piece of information that we can solve for. Well, this one's already solved for y, so half the work's already been done. Y is by itself on one side of the equals. So it'll make it really easy for us to just take this and use it in place of y in the second equation. So that's what we're going to do. I like to keep my system together. I'm just going to copy it down here, but I'm also going to take this part and substitute it where the y is in the second equation, like that. And then we're going to simplify. Okay, so we'll start by distributing the -3 here. So I'm going to be copying this down again, so we'll see the new version of our system down here when it's simplified. Okay, so I'm going to just move this out of the way. And so if we do -3 times 4x, we'll get -12x. Okay, then if we do -3 times -5, we'll get +15. Now we want to combine like terms. Notice that we have 12x minus 12x. So what does that work out to? 0 times x. And 0 times x is simply 0. Then, of course, 0 plus 15 is just 15. So this is where students usually get confused. They may have done the work all correctly, but they're not sure what to do with this. Now, if this ever happens with a system of equations, that means that it's one of the two special cases, right? Either they're the same line and they intersect everywhere, or they're completely perfectly side by side and never ever touch and don't have any solutions. So if the way you can tell is when this happens, when the x's and y's are all gone, you get a true statement. If you get a true statement, it means they're the same line and they intersect everywhere. And it intersects itself everywhere. Oh, it's a weird way to say it, but basically all real, not all real solutions, but infinitely many solutions. Okay, so a true statement without any variables that means you have infinitely many solutions. But it's not all real solutions, or it's not all possible, it's not all points that you could ever graph on an xy plane. It's specifically just the points that lie on this line, right? If I back up to this version of it and notice that there's a common factor here in the green equation, all of these, the 12x, the negative 3y, and the 15, can all be equally divided by 3. So if I divide everything by 3, watch what happens with this equation over here. So if I divide 12 by 3, I get 4. If I divide negative 3 by 3, I get negative 1. If I divide 15 by 3, I get 5, right? Now, if we were to solve this for y, like the top one is solved for y, what would we do? We would subtract 4x from both sides so that it would be gone from this side, right? And then we would divide both sides by the negative 1 here, right? So that negative 1 here has to be divided out. So I'll have just positive y. So if I divide by negative 1 here, I get regular y. If I divide by negative 1 here, I get positive 4. If I divide by negative 1 here, I get negative 5. So see how they actually are the same equation when you simplify it like this? Yeah, so it's one line, and all I have to do is express this relationship between x and y in my ordered pair. Okay, so if it says in terms of x, that means that the first box is going to have x in it. Let me get a color here. X. Okay, now the second box is going to be y in terms of x, meaning this. This is what y equals when you describe it, you know, that's equivalent to y, I guess is an easier way to say that. That's another way of expressing y, or how you get the y coordinate, right? 4 times x minus 5 is the relationship that we have on this line, right? So that's it. That's how you enter the answer. Now, if it had said write it in terms of y, that would be slightly different, and all we would want to do is solve this for x, and we would have y in the second box and then the equivalent expression of x in the first box. So let me show you what that might look like, or what it would look like for this example. Do I need to really start over? So yeah, probably for the best. So I'm going to just do that over here, and I'm just going to change this to say, what if it said, instead of in terms of x, what if it said in terms of y? Now, assuming that we already figured out that both of these turn out to be the same line, y equals, what was it? 4x minus 5. Can I draw? Hello? There we go. I'm writing with my mouse, so please excuse, it's not beautiful, but it's not too bad either. All right, now what I want to do is solve for x. And I'm going to do that by typing down here. It's a little faster. Okay, so y equals 4x minus 5. Now I'm going to solve for x. So what am I going to do? I'm going to add 5 to both sides so that I get this. Then I'm going to divide both sides by 4. So then I get y divided by 4. Or I could just say the whole quantity y plus 5 divided by 4. I could just say that. and x would be alone, right? So what I would write as my answer, since it says in terms of y this time, I would write y where the y normally goes. So y is just whatever y is. We're going to talk about x once you have a y value. You can take the y that you already picked, add 5 to it, and then divide that total by 4, and this will give you the corresponding x value that would land on that line. So now putting in that expression here, I would just write y. I would use the fraction feature when entering my answer. I would do y plus 5 over 4 like this. Okay, and to see that this is true, like if you were to actually graph that line, if you were to actually graph this line, let's say oh, I should have made my, let's bring it down a little more like this. If we were going to go and graph 4x, y equals 4x minus 5 using the slope-intercept form, we would go down 1, 2, 3, 4, 5, and do our y-intercept. I'll use green just so it's different looking. Also move this highlighted box out of the way. And then I would use my slope to go, the slope is 4 here, so I would go up 1, 2, 3, 4, and over about 1 right about here, right? So I would have a line going through those 2 points, okay, something like that. Now every single point on this line will share that relationship, every single one of them. Like if I just look at this point right here, this has the coordinates. Let's draw it on there. Can I draw? 1 for x, and what is that? -1 for y. Right, now let's see if that works with this relationship here, right? So if I take an x value of 1, let's plug it right into, we'll plug it right into here. Or we could even use this version. We could use either version, right? But if we plug it into this version, what we have is y is supposed to be -1, and 4 times +1 minus 5. Okay, so what I should figure out is that when I simplify this, I get -1. So it's going to give me a true statement. It's going to satisfy this equation. Right, so let's do that. So let's see if I get -1 when I take the x value of +1 and multiply it by 4 and then subtract 5. Notice that 4 times 1 is +4. 4 minus 5 is -1, right? So that's a true statement. So it satisfies that. Same thing if I did it down here, right? If I did the -1 is the y plus 5, and then divide that total by 4, will I get +1? As I should, according to this ordered pair, which falls on the line. And let's see what happens if we simplify this. The -1 plus 5 simplifies to +4. +4 divided by +4 is +1. So we get a true statement again. So that's another example of, you know, how this coordinate, this point right here, is a solution of this line because it satisfies it, right? All right, so I hope that helps, and I'll see you in the next video.